Welcome back to this course on C programming and assembly language. We are currently in module 2, which deals with C programming and inline assembly. In the last couple of lectures, we discussed some elementary way of interspersing inline assembly instructions with C programs, and we discussed how to, for example, evaluate an arithmetic expression in terms of variables and put them into registers. Then we later on implemented a multiplication program in assembly language using looping, right, using the jump or no zero kind of instructions. So let's proceed in that direction, and in this lecture we will discuss some ideas on converting C programs to assembly language, both in an optimized and unoptimized manner. So let us start with a very simple example. I want to divide two integers and put the value x by y, right, in the variable z, and the remainder, right, x% into a variable called r, and I want to implement this in a particular C program. So now let us look at the C implementation first, and then we can go ahead and look at the assembly implementation. So the C implementation is as follows: main, and I have int x, let us say, equal to 10, y equal to 20, then int z comma r. So how would I do this? I would simply say z is equal to x by y and r is equal to x% y. Of course, you could choose to print these values after this program, but let us leave out those aspects for now. So let us first look at a very elementary way of implementing or translating this program into assembly language without any optimization. So therefore, we look at the following statements. There is int x equal to 10 and y equal to 20. So this is basically a declaration of x and y as integers, which are each going to be 4 bytes, right, 32 bits long. But we are also initializing these variables with values of 10 and 20. So if you look at the assembly instruction, then this particular instruction would get translated into the following, which is basically move x comma 0x 000a, right. It is a 32-bit number, but I am leaving out the trailing zeros here, and move y equal to, or there is no equal to, sorry, move y comma 0x 0 0 so 16 plus 4, right. Yeah, this is basically 20 in hexadecimal. Next, there is a second statement which is basically int z comma r. So here we are not initializing any of these instructions with or variables with any value, and therefore this will really not translate into any particular assembly implementation. Next, we move on to the statement z equal to x by y, right. So we have the statement z is equal to x by y, right, and both are integers. In order for the microprocessor to perform a division instruction just like multiplication, you have to use the EAX register implicitly, right. So just to remind you of what happens, you have to you can say div EBX, then what would happen is EAX would get the quotient by EBX and EDX would get the remainder EAX remainder EBX. So, in order to perform a division operation, I need to set up certain registers first. So, therefore, I go ahead and first move EAX with X, right. EAX simply gets the value X. Now, I can go ahead and perform a division instruction on this EAX, right. So, I can say div of y, whatever this y is, let us not worry about it for now, right. It is an abstract entity for now, where I have a variable in which I can read from or write to some particular value, right. And because these are integers, note that the instruction that actually gets implemented in assembly has to be the instruction called IDIV, which is basically integer division or signed division that has to be done, right. So, in the end of this particular operation, what would have happened is EAX would have got X by Y quotient, right, and EDX would have got X percent Y. Reminder. So, now I need to go ahead and initialize my Z with the quotient, and therefore, all I have to do is move Z comma EAX. Z is equal to quotient. So, we then move on to the next assembly instruction, right, the next C instruction, which is Z is equal to X percent Y. So, here again you have to do another division operation in order to obtain the quotient, and sorry, this is not Z, this is R is equal to X percent Y. So, note that this division operation or the remainder operation in C could have been done with any two other variables. So, typically if you look at an unoptimized compiler output, it would not worry about if these registers have changed or not from one C instruction to the next, and therefore, it would go ahead and set up this division much the same way as it did in the previous C instruction. So, it would repeat exactly the same thing, EAX comma X, right, then it would do IDIV Y, and the result of this is that EDX will now have the instruction or the value of the remainder. Now, on finishing this instruction, all I have to do is move R comma EDX. So, this is nothing but the variable R getting the remainder. So, what you notice here is that there is a lot of redundancy in the instructions that are generated for an unoptimized compiler output, right. For example, you see very clearly that when I finish my operation here, EAX and load EAX with X and IDIV with Y, EDX has already been evaluated, and hence there is no real need for me to go ahead and perform this second division operation. So, that is the crux of unoptimized compiler output and optimized compiler output. So, if we were to go ahead and do this particular translate this particular C program into assembly, then this is what we would have done, right. So, we have int x equal to 10, y equal to 20, right? This would simply translate to two instructions, move x comma 0x 0 0 move y comma 0x 0 0 1 4, right? And then there is the next instruction, which is int z comma r, which basically translates to nothing in assembly. Then the z is equal to x by y, and r is equal to x percent y would simply translate to the following instructions, which is move eax comma x I div y, move z comma eax, move r comma edx. And so what we are effectively doing is we have only one set of division operation that is being done as shown here. On the other hand, the unoptimized compiler output has two division operations that are being done, and the reason for that is you are just taking line by line and just translating it blindly into the necessary assembly that will result in the correct output. We are not trying to keep track of the contents of the registers between two instructions. Let us now consider another example in order to look at this concept of optimized and unoptimized compiler output. So let us consider this C program. Main, I have int a, b, c, d, and int x equals 10 and y equals 5. So let us say I want to do the following: a equals x plus y, b equals a minus y, c equals b into y, and d equals c by y, right. This is the quotient, by the way, right, just to remind you, this is the, because we are talking about integer arithmetic here. So let us look at an unoptimized compiler output first, which basically is simply going to take line by line of the C program and just translate it to its corresponding assembly output, right. So you take this statement, because there is an assignment happening, this will simply translate to move x comma 0x 0 0 0 a, and this, the other one will translate to move y comma 0x 0 0 0 5. So now let us look at the first evaluation that we want to do, which is basically a equals x plus y. I want to now look at the assembly output of this block. So in order to perform any ALU operation, I need to move certain operands into registers. So therefore let me arbitrarily pick EAX as my register, and I am going to move EAX comma x, right. So what does this instruction do? EAX simply gets the value x, and then I am going to perform an addition on this, which is add EAX comma y. So what does this do? EAX is simply going to be EAX or that already has x, so it will be x plus y. Now I need to move this sum into my variable a, so I will do move a comma EAX. So a will get x plus y here. Now let us look at the next C instruction, which is b equal to a minus y. So I want to just blindly translate this into some set of assembly instructions which are correct. So what do? We move again this instruction, this time let me pick bx, ebx comma a, and then I will directly do a subtract ebx comma y, and then move b comma ebx, right. So what am I doing here? I am loading ebx with a, I am loading ebx with a minus y, and here I am saying b is a minus y. Similarly, if you go ahead and translate the next instruction, which is basically c is equal to b into y, I mean I have to store one of the operand in EAX. So therefore I will say move EAX comma b, and I will simply say I mul y, right, and in the end of this instruction I could simply say, let me just get some space here, move c comma EAX. Similarly, you can do it for the fourth division operation as well. So the key point here is that if we just blindly translate every C instruction into assembly, what you will get is a very unoptimized output, in the sense that there are a lot of move instructions which are severely redundant in this process. For example, if you look at this particular instruction, move ebx comma a, is totally unnecessary because EAX already has the right value in the previous step. So if you look at this guy, the previous step already has the value of a in EAX. So without loading anything into EBX, you can simply subtract directly from EAX and obtain the value of b, right. Now similarly, if you look at this particular operation now, it is totally redundant because we are unnecessarily loading the value of b again into this EAX register and so on. So let us now look at what an optimized output is like by considering what the contents of the register was in the previous instruction, right. So we will now look at optimized output. Okay. So what I want to do is x plus y, b equals a minus y, c equals b into y, and d equals c by y. So what I am going to do is, because the multiplication and division typically needs EAX, I am going to simply deal only with EAX as my primary operand throughout. So what do? I first move EAX comma x, and I simply do an add EAX comma y. So, this is EAX is x plus y. Now, since my EAX already has the sum x plus y or the variable a, I do not need to move it explicitly into another register before starting the next instruction. So, what I will just do here is I will just move my EAX into the variable a, right, but EAX still has the sum x plus y, and therefore, now I can simply go ahead and do subtract EAX comma y. So, what does this do? It simply does EAX is a minus y, and now I just have to move this result into the variable b. Now, similarly, I go ahead and perform my multiplication operation directly here on I let me call it I mul of y. So, what is this? This is EAX is what? It has the value b into y, and of course, I move the value from EAX into the variable c. Now, I go ahead and perform my division as well, because the value of c is already in EAX now. I div y, which implies EAX now has the value c by y, and of course, I move the quotient into the variable d, and the quotient is available in EAX. Now, note that I could, for example, add another thing which is c percent y, which implies without adding any new instruction, I can simply go ahead and let me not call this d, I will call this e, another variable, and I will simply add another instruction here, move e comma edx. So, what you see here is we have got rid of so many redundant move operations in order to optimize this assembly code. So, you must realize that unless you use a compiler in a particular optimized mode, it may not be possible to always get the most optimized and quickest instruction set in the assembly level.